Okay, good morning, everyone. Nice to see you. Thanks for coming. Well, this is the course on black holes. And I'm just today, I'm going to start with a few introductory things and then get in. Now, here's the outline of the course. Black holes are certainly the most dramatic, most interesting thing happening in astronomy right now. And one of the most interesting things in all of science, I think it's fair to say. They're absolutely changing what we know about the universe. For a long time, black holes were thought to be a sort of a strange thing that we weren't even sure they existed. Now we know they exist. But not only do they exist, but they dominate many aspects of the universe. The formation and the evolution of galaxies. We have a huge black hole in our own galaxy, changing everything. So black holes are really top-notch science right now. Now, the outline, we have 5 lectures. The first today won't be very much about black holes. It'll be about gravity. But black holes are the extreme manifestation of gravity. So we need some background in gravity to understand how black holes form. The second lecture will be the Schwarzschild black holes. Black holes were theorized long before we detected them. And that will be the subject of the second lecture, and then as well as the first detections of black holes and how we did that. Third lecture will be supermassive black holes. There is a monster in the center of our own galaxy, a black hole which is millions of times bigger and more massive than the sun. And the sun is 300,000 times as massive as the Earth. But this black hole dominates everything. It's gigantic. And it's not even the biggest. Then in 2019, I think it was, we got the first images of the shadow of a black hole. So now we kind of know what they look like. We have really strong evidence. Fourth lecture will be gravitational waves. These black holes sometimes smash into each other, and they smash into each other with such enormous energies that space itself wobbles. Space wobbles. And those are called gravitational waves. We'll talk about that. And finally, the last lecture will be, since the launch of the James Webb Space Telescope in 2022, we have gotten a completely new vision of the very first years of the universe. First 100 million years, 200 million years of the universe. And we're seeing how the very first objects in the universe formed. And to our amazement, black holes dominate that process as well. So we'll talk about that, and then we'll talk about a little bit about where the future is going to be. It's not going to be dark, is it? Not because of black holes. Okay. Let's see. There's a lot of literature here. What this was supposed to say is, yeah. Click on more. I'm a hide here. What this? One more. That's it. Okay. Yeah, this is tiny on here. So. And then click OK up on top. All right. Okay. Okay. Now. There's a way I'm going to do this. I tried this 2 years ago or a year ago, and it's kind of worked. Because I have a very diverse audience. Some of you have never had any science. A couple of you I know have a PhD in science. So I'm trying to reach everybody. And so the way that I'm doing it is that most of this course is for everybody. It's going to be roughly at the level of a NOVA presentation on television. But occasionally, to keep the nerds interested, and I mean it's a compliment, I will do something harder. And I'll mark that with this cat. Okay, so when you see that cat, it's something harder. But don't worry about it, because I'll soon get back to something easier. So this isn't like like a scary math course where it keeps getting harder and harder as you go through the semester. I'll do something you don't get, and don't worry about it. Pretty soon I'll come back to something that you will get. Okay? All right. Well, that killed it. Now I can't advance anymore. Just click the screen. Ah, that worked. Thank you. Okay, so today I'm going to start with Isaac Newton and the force of gravity, classical stuff that was done about 300 years ago, and how gravity works in the universe. And then we'll take a break, and after that, I'll talk about the changes that Albert Einstein introduced in our understanding of gravity around 1915. And then I'll talk about gravity and light, which is crucial to our understanding of black holes. Okay, everybody knows the story of Isaac Newton and the apple. The story is actually true, or probably true, at least Newton told it. So, and the idea was not that the apple fell on his head, but that he saw an apple fall, and it occurred to him that what was making the apple fall was the same thing as what was making the moon go around the earth. So he made a connection between those two things, an apple falling and the moon going around the earth. Everybody had seen that for tens of thousands of years, but he was the first person to make the connection. It could be the same thing, that there was a force that was attracting the apple to the earth, that was making the apple fall. And see, that whole idea was new. Before Newton, I think, when you read the Greeks, I mean, falling is a natural thing that happens, right? That's how people understood it. That's how I think we understood it as children. But Newton had the idea something was making the apple fall, and that same thing was making the new moon kind of fall to the earth in a sense, making the moon move. So that connection, that was new. And it's important also to realize, some of you who took physics know there are Newton's laws of motion, that, for example, something will continue to move without stopping unless there's a force to stop it. So on a perfectly frictionless ice surface, you'd scoot forever. That it would take a force for you to change that uniform velocity. Now that was already understood by Galileo, and he specifically said it. And Newton added, and this was also known to people, that in order to change the velocity, you have to have a force, and that force causes acceleration. But what was really new was Newton's understanding of gravity. That was utterly new. In fact, he coined the word gravity. Gravitas, I think, a Greek word for heavy. Well, this is the apple tree. The apple tree died or was uprooted and fell a few times, but they took cuttings and replanted it. So this is the descendant of the apple tree that Newton saw. And we planted that same kind of an apple tree at Penn State, and it's now starting to make apples. And the apple is called the flower of Kent. It's an apple, you actually can't eat it. It's not very good, but it was used for cooking in those days. We couldn't, we wrote to England to try to get a piece of the original apple tree, but you can't import this sort of thing in the United States. So there's a nursery in the United States that sells the same type, and so maybe this one's distantly related to Newton's apple tree. Okay, that was just for fun. So this is Isaac Newton, and so let me just repeat what I said. The force of gravity is such that all masses are attracted to all other masses in the universe. Everything is if it has mass, it's attracted to other masses. You're attracted to other people in this room by gravity, but the gravity force is not strong enough for you to notice. The friction where you're seating is greater than the gravitational force that attracts you to the person sitting next to you, so you don't move towards them. But you are really attracted to the Earth because that's a huge mass. And the gravitational force is dependent upon the mass. Bigger masses have more force. And the force gets smaller as you get further and further apart. So this is actually the earliest picture of Newton that we have when he was in his 40s at this time already. But this is an actual portrait of Newton that was painted in his lifetime. In fact, it was in his house, they said. So, okay, so this is the way the force works. If there are two masses, a little m and a big M, they attract proportional to the product of those two masses. And they also attract proportional to the inverse square of the radius, of the distance between them, right? The distance between them. So if it's twice as far apart, the force is 1/4 as strong. If it's 3 times as far apart, the force is 1/9 as strong. And it's also proportional then to the mass. Okay, so, well, I can't resist doing an equation, even though I've been warned if I put in equations, people will leave. But this is just for this is just for those who want to see it. And even if you've never seen an equation before, you can see that this force is the two masses divided by the distance between them. It's not a very complicated thing. The big G just gives the strength of the force. That's just a number that you measure. Now the big thing about this is that it is a force that goes through empty space. There's nothing between us and the sun, but the Earth is attracted to the sun. And so, and that bothers people a little bit sometimes. It's not a push or a pull, although those are also forces. This is a force that's transmitted through empty space. Now, it shouldn't, I don't know why it kind of bothers people a little bit. I mean, magnets do the same thing, right? They attract and there's nothing between them. So this is a force or a field force that goes between things, even if there's nothing between them. It's not a direct push or a pull.
Softball question for you. What's the difference between mass and weight?
What's the difference between mass and weight? Mass is a property of an object. The weight is the force that it has when it's near the Earth, but it will have a different weight on the moon, but the same mass. So and in this equation, the weight is F and the mass is M. Okay, so don't panic, all right? I'm not going to ask you to calculate anything. Oh, yes, and when I was drawing that cat, I asked ChatGPT to come up with a picture of a cat scared of an equation, and this is what it came up with. Okay. But it's amazing that it could do that. I mean, I literally asked it, can you make a picture of a scared cat looking at an equation? And this didn't work instantaneously. It took it about 2 or 3 seconds to come up with this. So it is an amazing thing. Okay, well, gravity is universal. And we see it all the time. It affects the tides, for example. The moon pulls on the Earth and the water differently, and so we have tides every day. That's an effect of gravity. And even if we were in a permanently cloud enshrouded planet, we would know there's a moon there because we would see the tides, and we could figure out that there has to be something out there that's causing that.
Roger?
Yeah?
So is the question, the Earth and tides are different because of the mass of the Earth versus the mass of the water?
Well, and the water is fluid, so it can move. And the part that's closer to the moon gets a little bit higher because it's a little bit closer to the moon, it's attracted. Part that's opposite, okay, feels less attraction than the Earth itself. So that's the second tide of the day, 2 tides a day. That's not totally obvious. Okay, Another example is, of course, the one I've given, the moon. The moon moves in an elliptical orbit around the Earth. And it's the attraction of the Earth on the moon that causes that. And the Earth is also attracted to the moon is attracted to the Earth. And this was, in fact, a historical thing. When Kepler, and I'm not going to go into the history of this deep, but Kepler had shown from observations that the planets move in elliptical orbits around the sun. And so that was known before Newton, that they move in elliptical orbits. And the story is, and it's apparently true, that Edmund Halley, another physicist at the time, known for Halley's Comet, was walking with Newton one day and said, how would planets move if there was a force from the sun which was inversely proportional to the distance to the sun? And Newton said, oh, an ellipse, I've shown that. And then Halley said, that's very important. That's critical. You must write that up. And Newton then sat down and wrote his famous book, The Principia Mathematica, where he introduced gravity and the laws of force and so forth. Okay. Well, here's the famous picture of the solar system. The ellipticity of the orbits is pretty small, and hard to show on a thing like this, except for Pluto. You can kind of see that Pluto is actually different from the other planets. And there was a lot of controversy about this, and people still ask me, is it a planet or not a planet? And Pluto is something different from the way the Earth and the other planets form. It's one of the Kuiper Belt objects. There are thousands of these things out there. Pluto's the biggest one. And so now I was at one of these discussions in the astronomical community, and half the group said, Pluto is a planet. It's a minor planet. And the other half said, it's not a planet. It's a minor planet. So, Okay, here's an interesting example, which we'll come back to. Sirius. Most people can recognize Orion in the sky. Here's the belt of Orion. Here's the shoulders. Here's the sword of Orion. Here's the feet. And below it is Sirius, the brightest star in the sky. So Jupiter and Venus are brighter, but they're planets, they're not stars. Sirius is the brightest star. It's the dog star. It's the only star mentioned in the Bible, as a matter of fact. About what was discovered in the 19th century, that Sirius has a companion that orbits around Sirius. And that companion makes this orbit. And it's an ellipse. It's gravity again. Okay, so now this takes half a century or something to go around. What happened here? Oh, this isn't working. Wow. So here's the dates. And we're about here right now. And then in 2048, it'll kind of come back to where it was in 2000. So it's an elliptical orbit. Here's a globular cluster. This is an object in our galaxy, 300,000 stars or so, all clumped together. Now, there's not a central big object. They're all, the gravity of one acts on the gravity of all the others. So on each other, and that forms a globular cluster, huge groups of stars. Now, they're not that close together. They're light years apart still, or fractions of light years. And the center is not a solid. It's just overexposed in the center. So there's still stars there. But again, it's all held together by gravity.
Maybe line in front of the 300,000.
Oh, approximately. That's a mathematical symbol, approximately 300,000 stars. This is the Andromeda Galaxy. This is a another vast group of stars. It looks like a nebula, it looks like clouds, but in fact, when you look in detail, and you can see in some closest, it breaks up into stars. And this Andromeda Galaxy is a grouping of stars composed of about 300 billion stars in a galaxy. And it's 2.5 million light years away. It's one of the nearest galaxies to us. So 2.5 million light years, that is, the light that you see took 2.5 million years to get to us. And that means it's pretty far away. The light from the moon takes about a second to get to us. The light from the sun takes about 8 minutes to get to us. So 2.5 million years. That's a long way. And we're also in a galaxy, which we call the Milky Way. And our galaxy is like just very similar to this one, just slightly smaller, about 200 billion stars. And so, but if there are people on Andromeda and they're looking at us, our galaxy, they would see something very similar to this. And they would, if they found the Earth, they would say the Earth is about out here in the suburbs someplace. Okay. Held together by gravity. And well, let me point this out. Galaxies like this, with the spiral galaxies, are big things, but they're thin. They're pinwheels. They're thin in one direction and big and round in the other direction. So like a big pancake. And you can see that if you were in a planet in this galaxy, if you look perpendicular, you would see pretty much blackness. But if you look in, you would see lots of stars. A hazy thing. Look in this direction. And we're in our galaxy, of course. And this is a picture of the Milky Way. And that's exactly what we're seeing. When we look in this direction, we see the disk of the Milky Way. When we look perpendicular, you see nearby stars, but fewer stars. This way you see lots. This is actually where the center of our galaxy is. It's not obvious at all from this, but that's the location of our galactic center, which I'll come back to. And
where's the black hole?
in the center of the galaxy.
It's in that.
So does it have mass?
Lots of mass.
Roger,
Yeah.
way back in the back. Since it takes so long for light to travel, that we have no proof that it looks like that right now, do we?
That's right. It has probably evolved.
Yeah.
Okay. Now, this is relatively nearby. The light from the center of our galaxy takes only 30,000 years to get from there to us. But that's nearby. You gotta, the universe is big. I mean, really, really big.
Roger.
I'll tell you what I said before, but a few months ago, I was thinking it's kind of a long way from the west side to the car wash on the 41st. But I'm telling you, that is nothing compared to the universe. Pardon?
Within the galaxy, it's all orbiting.
Yes, the galaxy rotates. The stars in the galaxy orbit around the center in that plane. Mm-hmm. Now it's not totally flat. There nearby stars affect it and so forth, so they can wobble around a little bit. But overall, the motion is in the plane like a big pinwheel with the arms trailing.
Black hole.
Nothing big except the black hole. And they actually move more under the effect of all the other stars than the black hole. Even though the black hole is very massive, it's not the dominant thing for that motion. Okay, we'll get more into that. Yeah.
And it's also true if you could look at, briefly speaking, of the whole universe, that all the galaxies are also moving.
Yes. All the galaxies are also moving.
Roger, are we able to calculate the mass of the black hole at the center of our universe or galaxy?
Yes, the mass of the black hole in the center of our galaxy is about is about 4 million. Sorry, just turn off your. It's about 4 million times the mass of the sun. And it's, I mean, I can convert that into grams if you want or something. It's easier to think of it as compared to the sun. Okay, let me go on a little bit. Yes, here it is. We can also look towards the center of our galaxy and see stars that are near the center of our galaxy. And here is a picture of the motion of stars very near the center of our galaxy over several years, about 15 years. And you can see they also make, you probably wouldn't say right away they're ellipses, but they're elliptical orbits. And from those orbits, we know there's something that's making those stars do that, even though we can't see it. And we can measure its mass. And so it looks like it's, and the mass that you get is about 4 million times the mass of the sun. So there's a mysterious object in the center of our galaxy. And I remember when these observations were first made, and people were saying, this is evidence for a black hole. And that time we didn't know there were black holes or massive ones like this. And finally, one person just got up in a meeting and said, look, this is either a black hole or something that's even weirder than a black hole. So, okay. So that's how we had to go through this. There was a lot of questions about this. Okay, well, here's a picture. I said the moon was falling to the earth. And this is actually a picture that Isaac Newton made. And he showed that if you threw a rock off of a mountain, see, and then the rock would fall. But if you threw it harder, it'd go a little further. And if you threw it hard enough, it would make a whole orbit. And it's in that sense that the moon is falling, the way the apple falls. Okay, it would fall straight, the moon would fall straight to the earth, but it has this tangential velocity. And therefore it just, and the same way the sun, that's why we don't fall into the sun, because we have this tangential velocity. Yeah?
Elaborate on the elliptical versus why it's not circular in terms of what if this.
Yeah, that is what you calculate from that inverse square law. And and that depends on the initial velocity, the initial tangential velocity, how fast that's going. If it's 0, then it'll go straight in, and you calculate that. I don't know how to make that more obvious. Okay, it was a big surprise because before Kepler and before Tycho Brahe, people said they were circular because God had created them, and God would only do perfect things, and the circle was perfect. That was the reasoning that people used. And then Kepler showed that it was not circular, it was elliptical. And so that was a big change in people's thinking.
The tangential velocity that you're referring to that all the objects exhibit, is that in theory traceable to the Big Bang?
No, it's not actually in this instance. It's traceable to the initial cloud that formed the solar system. We know, stars and planets have to form out of something. And initially there was a big cloud of dust and gas, which by gravity condensed down. But that initial cloud had some rotational motion. And that rotational motion is what we still see today as the planets orbiting the sun.
So it hasn't dissipated,
That's right. It's hard to get rid of that motion. So it's an initial condition. It's different for every solar system and every planetary system in the galaxy. I mean, we now see about 6,000 other systems, and they're all different. So it's an initial condition that's not something that just is kind of happened. I mean, you can think about how mountains form, and so on. But there's a lot of initial conditions. Every mountain forms differently, and that's sort of the way these solar systems work. Yeah, one more question now.
Um, if electrons go around the atom and so planets go around suns and galaxies and move, does the black hole also move through the universe?
Does the black hole also move through the universe?
Yeah.
Yes, well, our galaxy is moving through the universe, and the black hole is moving with that. Okay, and in that sense, black holes are not strange. I mean, they have a mass and they move, and they attract other masses. Good. You guys are getting ahead of me. You're too smart. Yeah. Okay. All right. Well, let me mention now, one way to understand black holes and understand masses is this idea of escape velocity. You know that it takes, you can jump higher on the moon than you can on the Earth because it's smaller. On the Earth, if you give something 14,000 miles per hour, it'll leave the Earth. Anything less than that, it'll go up, stop, and fall back down. That's the escape velocity. Velocity, you have to give something at the surface of a planet to get it to escape from that planet. And so on the Earth, it's 11 kilometers per second. The sun is much more massive, so it's 618 kilometers per second. 11.2 kilometers per second is 14,000 miles per hour, so more familiar. There are odd stars. That companion of Sirius is a white dwarf, and they're extremely massive, small, dense objects, and there the escape velocity is 5,000 kilometers per second. 5,000 kilometers per second. And finally, there's a black hole where there's no escape. We'll come to that. But so a small thing like Ida, you could actually jump off of it. Okay. Okay. This is also the reason why planets are round, by the way. The planets are round because, well, it's sort of the same question of how high can a mountain be? Turns out on the Earth, Everest is about as high as a mountain can get. It can get up to about, I think, 5,000 feet higher than Everest. But then the gravitational force of the rest of the Earth pulls it down, and the rocks are not strong enough to counteract that. So it's like when you were a kid and you were building a sandcastle at the beach and you used wet sand. You could only pile it up so high before it'd flow up. And that's the effect. And so what happens is if you have small objects, like this is a very small asteroid, it's called Donald Johansen, and it's not round, or neither is Ida. It's 60 kilometers. But once you get up to something like 500 kilometers, then this self-gravity starts making things more spherical. And by the time you get to Ceres, it's pretty round. So that's why they're round. The gravity is enough so that you can't maintain mountains, high mountains on that. They'll flow. Okay, so that's escape velocity. So what, 14,000 miles per hour. So what kind of an object would it be if you had the velocity of light? Okay, the velocity of light is 186,000 miles per hour. Okay, 300,000 kilometers. 3 times 10 to the 10th kilometers per second. So 300 billion kilometers per second. Doing this right? 300,000, I'm sorry, that's centimeters. 300,000 kilometers per second. I've got the right number here. I misspoke. Okay, that problem actually occurred to a John Mitchell in England in 1783, and he took what he wrote here. And you can read it, but he had a sort of different view, but he said, if you take something like the sun and with its same density and just make it 500 times bigger, then the escape velocity would be so big that it would be the velocity of light, and light couldn't escape. It would be dark. So he had that thought in 1783. Now, we don't think of black holes like that today, but he had the right idea. And he published this and came up with this thought that there might be objects that are so big that we couldn't see them. And in this same paragraph, he wrote, the way we might detect them, though, is that they would have still gravity on other things. And even though we didn't see the object, we could see things orbiting them. And that way determine the mass of the object and that it's there. This, I have a question mark here because I used to show this, but then I read later that they're actually not sure that's really his picture. So, I hope that's okay. So now today we look at this slightly differently and a little more like what they really are. If you took the sun and shrank it to about 3 kilometers in size, then the escape velocity would be the velocity of light. All right. So here is a comparison of the sun and the earth. This is how big the sun is compared to the earth, right? It's really big, really small. But and I love showing this picture because I saw, well, not this picture, but a similar picture when I was in the 5th grade, and it really impressed me. All right. This huge Earth that we're on, all the centuries of exploration and the galleons in the Pacific and all this is tiny compared to the sun, even tiny compared to a sunspot. But if you took this whole sun and shrank it down to about this size, that would be a black hole. Then it wouldn't escape. Put all that mass into that small thing. Seems impossible, doesn't it? But that's what it would take. Yeah.
So we're getting to how black holes are formed. So I was wondering, does the gravity continually pull on everything to the point where it ends up like a black hole? Is that the idea?
Yes. But the sun, even though I'm showing it, we have to be careful here. The sun itself will probably never form a black hole. Okay, but more because there will be internal forces that prevent that total collapse. It'll collapse to a small thing, but not a black hole. But there are more massive things bigger than the sun that can collapse to a black hole. But I'll get into that a little bit more later on. Okay, I'd like to just talk a little bit about gravity because there's a famous statement by Newton that I'm going to read because I think it's really shows a lot. I've not as yet been able to discover the reason for these properties of gravity. See, I've just told you how gravity works. I haven't told you why it's there. What does it? And he says, I have not yet been able to discover the reason for these properties of gravity from phenomena, and I do not feign hypotheses. Today, I think we'd say, I do not speculate. For whatever is not deduced from the phenomena must be called a hypothesis, and hypotheses, whether metaphysical or physical or based on occult qualities or mechanical, have no place in experimental philosophy. In this philosophy, particular propositions are inferred from phenomena and afterwards are rendered general by induction. That was the revolution started by Copernicus, Brahe, Kepler, Newton, Galileo, that we would not speculate, we would not count how many angels it would take to move the earth around. We'll start measuring things. And that's what changed science. It was Tycho Brahe himself. People had been speculating, what makes the planets move? Are the orbits round? Why aren't they round? Are there round things that can make into elliptics and so on? Brahe said, he didn't literally say this, but his thinking was, let's measure them as carefully as possible. And maybe if we make really careful measurements, that'll tell us something. That was the change. Okay, I thought this was kind of fun. This is a graffiti of Isaac Newton scratched this into the windowsill of his schoolroom when he was young, and we still preserve that. This really is his signature. Okay. Okay, let's take a break for a few minutes. Okay. I got so much into AI that we have only those two pictures of Newton. So I asked AI, what would Newton have looked like when he was 25, when he did all this gravity work? He was only 24 or 25 years old when he invented gravity. And this is what AI came up with. 3 seconds. That's what Newton would have looked like, they think, at 25. Isn't that amazing? I mean, and it took it seconds to do that. Now, it wasn't instantaneous like most of the questions you asked. It actually took it a few seconds to do this. Oh my gosh. Yeah. All right. Okay. The mic is off. How do I get it on?
It's on.
It's on.
Roger, you're on here, yeah.
Okay, they can hear me.
On Zoom we can.
All right, I'll yell. Okay, so gravity feels very strong because we're near a very massive object, the Earth. But in fact, gravity isn't always the strongest thing. And this is just an aside, actually, it's not really critical for the course. But when you look at, say, the interior of the atom, somebody mentioned that earlier, the electrical forces are vastly greater than the gravitational forces between, say, two electrons. Okay, gravity is basically a weak force, even though it dominates the universe. But it's weak in the elementary particle realm. Electrical forces and nuclear forces are much stronger. Okay, now Albert Einstein in 1970 had a thought, and he wrote, "The gravitational field has only a relative existence, because for an observer freely falling from the roof of a house, at least in his immediate surrounding, there exists no gravitational field." Okay, so you don't feel gravity when you're feeling thing. And so he had this kind of a thought experiment. Yeah, the thoughts, Einstein worked a lot with thought experiments that you couldn't really do, but he could think his ideas and get his ideas going by imaginary experiments that he thought. And physicists like to use the German word Gedanken for that. And if you want to feel sophisticated, you can talk about Gedanken experiments. Okay, so imagine an elevator or a rocket ship in interstellar space, far from any source of gravity. Now, and you know that in such a rocket ship, you would float. And the apple would float. But if there were a sudden pull on the elevator, an acceleration, then the apple would fall, and you would feel a force to the surface. And Einstein said that is the same as gravity. That is how gravity seems to work. So that's a new concept. It's not totally obvious. But you know, this is exactly what would happen. And Einstein put this into the form of a principle of equivalence. The effect of a uniform gravitational field are locally indistinguishable from those of uniform acceleration. So that was his new way of looking at gravity. And this had another consequence. Because now imagine this. You're in this elevator, far from anything, and you shoot a light beam across the elevator, and it goes straight across. But now imagine that there was a sudden acceleration, pull on that elevator. Then as that accelerates, the light beam would appear to go down. And now from the outside, it would look like this, but inside, you would think it was a gravitational field. And from that, Einstein intuited that light would be attracted by gravity. And that was new, because in Newton's theory, light having no mass, at least no rest mass, but no mass, it wouldn't be affected by gravity. But Einstein introduced the idea that light would be affected by gravity. Now, someone in the break very wisely mentioned to me, didn't Mitchell have to think that light would be affected by gravity? And he did. So that's a good point. So let me hold questions for a couple of minutes, okay? Because I need to get a little further along here. And so this could actually be tested, because the effect is small. But if you had a star that passes near the sun, then the light beam would be bent by the gravity of the sun. And the star would appear at a different position than when you observed it when it was far from the sun. That was and Einstein predicted that. Because here is a letter that he wrote to Millikan at Caltech, and here he drew the picture that there's a star, and this is sun, and it passes near the sun and is bent. And he asked Millikan, could you observe this during the day rather than in an eclipse? And Millikan said, no, you really would need an eclipse. You can't do this during the day. But so there's Einstein, that's Einstein's prediction in 1912, I think it was, or so. And the funny thing about this letter is that the 84 seconds of arc is actually wrong. And Einstein got the right answer, which is twice as big 2 years later. So for once, nature was kind of nice to us and made it a little bit bigger than the simple calculation. It made it easier to observe, okay? A second of arc is a very small thing. So it's a small effect, but it's real. And Eddington proposed to do this at the next solar eclipse. That was in Brazil, I think it was. They went to Brazil, and they observed the solar eclipse, and then they observed the position of the stars. Those are marked here. And to see if they had moved during the solar eclipse when those stars moved, when the beam from those stars was close to the sun, compared to what you would see when it was far from the sun. So now it's a difficult measurement, right? You know, solar eclipse lasts 2 or 3 minutes. You got to get the whole thing right during that time. And lights are all askew. They found it. They, in fact, did move. And Einstein's theory triumphs. Stars are not where they seemed or were calculated to be, but nobody need worry like that. Okay. I also like this. Men of science are more or less agog. I didn't know there were degrees of agogness, but so anyway, so that's, you see the path of the eclipse. Eddington was in Brazil for this measurement. That was the setup they had, and he measured the motion exactly as Einstein had predicted. So this was new. So light is attracted by gravity as though any mass is. So we don't see it in everyday life because it's a small effect, and you need something big like the sun to really make it happen. But that was something clearly new. So light is attracted by gravity. That and the difference that I mentioned earlier, there's a kind of simple way to calculate that how much the deflection should be, and you get that 0.84 arc seconds, which Einstein first got. But when you do the full theory of general relativity, it comes out as twice as big. That's a difficult calculation. Okay, and then Einstein took another big step, and one that isn't obvious, but he reasoned that one way to look at gravity is to think of it as a distortion of space. And this is a way to look at it. Now, this is where things get, you have to really start imagining things, okay? Now, we're in a three-dimensional space. Now, it's hard for us to imagine a curved three-dimensional space because you have to go in the fourth dimension to visualize it, right? But and nobody's ever been able to do that. So the examples I use will be a two-dimensional space, okay? And that's distorted, and we can see that because we're in the three-dimensional spaces. You can see the distortion. So imagine this as kind of a tabletop or a tablecloth, or a rubber, maybe a rubber sheet, and you put something in it, an object, and it distorts the space. Then other objects that move around in that space will be affected by this different shape of space. Okay? That was Einstein's thinking. That is how he thought of his gravity. So it's a deeper thing than Newton had. Newton had no explanation. So this is the force I measure. This is what it is. Now Einstein has an explanation for it that is a distortion of space-time. And so to make this clear, again, this is a two-dimensional space that I'm imagining, like an ant moving around here. And then the ant sees there's a distortion of space, but it would interpret it as a force. Something's attracting me to this object. Ant wouldn't have the imagination to think of the third dimension, which we do. But it's hard for us to imagine the third dimension curved, because to really visualize it, you have to go in the fourth dimension. Actually, you have to go in the fifth dimension because it's space-time. That's okay. I think it was Leonard Susskind at Stanford who always asked his class, how many of you have been able to imagine the fourth dimension? Of course, nobody has, but there were always two or three guys who did this. Okay. So this is the idea that the masses distort space. Okay, now can we play this?
I think you play this, and I think you out of the presentation is going to go to YouTube.
There. Okay. Well, let me just do it. And
Yeah.
okay.
Let's talk about gravity. This is space, and this is the sun. The sun has so much mass that it warps the fabric of space-time. Now, planets go around the sun, and the closer a planet is to the sun, the faster it's going. But the further away, the slower it's going. And that creates this oval shape as the planets go around the sun. That oval shape is called an ellipse.
Okay, so that's an example. Oh, no. Yeah, but how do I go back to my slide? Yeah. It'll just come back on. It'll open back where it was. Okay. Yeah. Okay. All right. So that's an example. It's an analogy. It's a way to think about it. It's not perfect. No, none of these analogies are going to be perfect, right? I mean, deep down, this only wouldn't work if it weren't for the gravity of the sun pulling down, and stuff. But, it's a way to think about it. So the Earth is moving in a curved space. Another way I like to think of it sometimes is that if you think of the Earth as a curved space, two-dimensional space, but it's curved, then imagine that a ship making a triangle would make a triangle on the curved Earth like this, and the sum of the angles was greater than 180 degrees. Those of you who took geometry know that every angle has 180 degrees. The sum of the angles is 180 degrees. So here, this is, would it be on a flat surface, but on a curved surface, these angles have to be bigger. The captain in 1492 doesn't know that the Earth is round. And he says, oh, the angles don't add up to 180 degrees. There has to be, what happened to my, oh, there's the island. There has to be something attracting me. It's the island that's distorting everything. It's the island is casting a force on me. That's the analogy, okay? And of course, if space, I say of course, but if space is distorted, then light moving on straight lines through the distorted space will also be curved. And that's why light is attracted to mass. Okay, all right. What time is it? Okay, anyway, okay, I'll take a couple of questions now. There was a few questions.
That example showed that the balls came and got closer and closer to the sun. And so is there a calculation as to when we are going to run into the sun?
Yeah, I think that has been estimated, but bad things are going to happen before that happens. The sun itself, actually, before that happens, the sun itself will become a red giant and will expand hugely and will come out almost to the orbit of the Earth. And our temperature will go up to about 3,000 degrees. And so we don't need to worry about falling into the sun. That will. But the good news is it's about 5 billion years from now. I think the worst news is that in only, I don't remember the number anymore, I think 500 million years, because the sun's getting hotter, the oceans will evaporate. So that's probably not good news for us either. Okay, so curved space-time. Space is curved or bent by masses. Objects move in that curved space. And we interpret that as a gravitational force. That's what the idea of general relativity is. Okay, so that's as far as we're going to go in general relativity. But that is a prediction, and the black holes, the whole thing, are predictions of general relativity. Now, we're not going to go into the mathematics of that. It's notoriously difficult. It's a very tricky theory, but it seems to be correct, and we can kind of try to understand the results of general relativity. There's a famous story of Arthur Eddington, the guy who did the light experiment, and the newsman said to him, "Oh, I've read that there are only 3 people who understand the theory of general relativity." And Eddington said, "Who's the third?" So, yeah. But Richard, in fact, there's Eddington and Einstein. But Richard Feynman said that can't be true. That fact. There was never a time when only 3 people understood general relativity. It isn't that complicated. As soon as it was published, maybe 10 people understood it, and then right away, many more people did understand it. There was a moment when one guy understood it, but not before he published it. Okay.
So you said that time is affected also. I don't know if you want to elaborate on that a little bit.
Yeah, that gets really complicated and off our subject. The way general relativity is formulated, it is not formulated the way Newton's theory is, just in terms of 3 coordinates of space, but it is formulated in terms of 4 coordinates, with time being the next coordinate. And that time is also affected by curvature of space, or curvature of space-time is the correct way to say it. And that's why you hear time slows down near a big mass, for example. So time is also affected. But let's do that for the second course. Okay, So I'm going to end here. Just a few things to take away. Gravity is a universal force. It acts between all masses. It's long range. It acts over the greatest distances in the universe. And Einstein showed that gravity is a bending of space-time. Objects move in curved space. And a consequence of curved space is that light is subject to gravity. And that's crucial for our black holes discussion, of course. That's okay. Let's see where I'm at. Oh, okay. So that's the end of the lecture. Next time we'll talk about black holes specifically. I'll take some questions now.
Yeah, just thinking about GPS, is that also affected by space-time?
Yes, absolutely it is. You have to, they make corrections to that.
Oh, they do.
Yes, yes, absolutely. And it was also a way to, at its beginnings, it was actually a test of general relativity. And they found that when they made those calculations, everything came out right. So general relativity is
Yeah, small.
small, but real, right? But I mean, because we're measuring, billions of seconds easily now. So, yeah.
That's what takes you.
Okay. Any other questions? Okay. Well, no. If not, that's it. Thanks. Take care.
Thank you, Roger.
Yeah.
Two quick questions. Number one, if